Hello everyone, it's Mr. Page again, and just jumping into another genetics tutorial. This one's on sex-linked traits, a little bit different than what we've had before in using monohybrid, dihybrid, codominant, incomplete dominant, in that every one of those traits there were always two alleles involved. And with sex-linked traits, it depends on your sex of how many alleles are actually available to the individual. And so just to get a little bit of definitions out there so everyone kind of understands what the sex chromosomes are. There's two types of chromosomes that we have. We have autosomes, which are all the chromosomes numbered 1 through 22, those pairs. So chromosome pairs 21 through 22. Now the 23rd pair are your sex chromosomes, and these things determine gender. So males are all XY, so they have an X chromosome and a Y chromosome. That's what makes us male. And females are XX. Depending on the species that you are, you can actually have different sex chromosomes determining your sex. Being XX and XY is inherent to mammals, and specifically there, of course, in this course, regarding humans. So if you ever hear about who determines the sex of the child, it's actually always the male who determines the sex of the child. Because females have only one chromosome to give in the way of the sex chromosomes. They only can give an X. That's all they can give. While males, on the other hand, can give an X or a Y. Now, you might say, well, why are we talking about inheriting chromosomes, big deal? Well, the thing is that the X chromosome is very gene-rich. There's lots of genetic information on that X chromosome. While the Y chromosome is really gene-poor. There's an SRY gene on it, which essentially makes you male, but it's a very gene-poor chromosome. And so you can kind of think about it, a male versus a female. The number of genes that there are, males are kind of lacking a few. If you look at it on the total numbers of genes, kind of all the genes and all the chromosome pairs, males have a few less. A little more variety, but a few less. So if we were to go ahead and kind of do a little Punnett square with just the chromosomes, as you can see, 50% of the offspring would be male and 50% would be female. Now, this is, I guess, mathematically how you could think about it, but it's not actually entirely true. The environment of the woman's vagina can actually determine sperm that have Y chromosomes in them, or sperm that have X chromosomes in them, can actually influence which ones can get to the egg faster. So the environment of the woman actually can skew that 50-50 percentage ratio from what you would normally think. So the genotype and the ratio, there are 1 XX for every 1 XY, hypothetically. And the phenotype in the ratio is 1 female for every 1 male. Now, the interesting thing is that some alleles are on these chromosomes. And as I mentioned to you before, that X chromosome is very gene-rich, while the Y chromosome is somewhat gene-poor. And they're different chromosomes in their entirety, obviously. So one of these traits that are considered sex-linked is a trait for hemophilia. And so in humans, the allele little h for hemophilia is sex-linked, and it's recessive to the big H, which is dominant for normal blood clotting. So sex-linked, what it really means is that the gene is found on the X chromosome. And so therefore, the chance of males in inheriting the gene is different than the chance of females inheriting. Scroll down here. There we go. Okay. So what we're going to do is we're going to let the X, representing the X chromosome, with the superscript capital H, represent the dominant allele for clotting, and the big X with the superscript little h, the recessive allele for hemophilia. And Y is just going to represent the Y chromosome. And since this gene is X-linked, it's a sex-linked trait, it is not present on the Y chromosome. So the males in this case are kind of dealt with whatever X chromosome that they received from their mother. That's the X chromosome, that's the allele on that X chromosome that they're stuck with. They don't have any other X chromosome to compensate for it if it is messed up. So in this case, it says cross a woman who is homozygous for normal blood clotting. So homozygous meaning the same. She's X big H, with a man that has hemophilia. So he's going to be X little h Y. And notice I didn't put the superscript H there for the Y chromosome because the Y chromosome does not carry the allele for hemophilia, for that blood clotting. So if we divide these up into gametes, you can see the female only has one option. She's going to give her offspring X big H. And if we plug them into the Punnett square, you can go ahead and fill this in. Of course, 50% of the offspring are going to be female, and 50% of them are going to be male. So in this case, all the daughters that this couple would have would all be X big H, X little h, so you'd be heterozygous. And there would be one of those for every male, and every male will be completely normal as well. So we have one normal female, and this female would be considered what we call a carrier, because she is masking the recessive allele. But phenotypically, we wouldn't be able to tell. The only way you could tell is thereby genetically. And we have one normal male, because he has dealt with whatever his mother gave him in the way of the X, because he inherited the Y from the father. What would happen if one of the daughter carriers marries a healthy man and they have kids? So one of the daughters, who is X big H, X little h, marries a healthy man, X big H, Y. So everything seems perfect with this couple. Male is normal, the female looks normal, and we set up this Punnett square. There are females, you notice, are normal, right? One's homozygous dominant, the other one's heterozygous. The male is normal there, but here we have a male who has hemophilia. Right? So this is the kind of the danger for males, at least, of not having that other X to mask it. So, what is the only way a girl could get hemophilia? Well, the only way a girl could get hemophilia is if she's X little h, X little h. If she had a father, who is X little h, Y, and she had a mother who was a carrier, or had a mother that also had hemophilia, right? She would get one of the H's, one of the X little h's from her mother, and the other one who is her father who has hemophilia, get that X little h from her. And another trait that is sex-linked is colorblindness. And this question here says, if a father is colorblind, what do you know about his daughters? Well, to answer this question, I'll tell you a little bit about my family. I am colorblind, and I'm going to use some pedigrees to discuss this with you. So I am, squares are males, so I am colorblind. So I'm X, we'll say X little b y. I must have put my y there. Now I have a wife. Females are going to be denoted with circles. And as far as we know, on her family tree, she is completely normal for color blindness. So we can assume that she's X big B, X big B. Now we have 3 children. We're going to denote this with kind of a little branching off here. I have a son named Trevor, a daughter named Kayla, and a son named Nate. Now for both of my sons, I had to give them the Y chromosome. That's what makes them male. They also received an X with a big B from their mother. So both my males, and every male that I would ever have with my wife, would be normal color vision. Now for my daughter got an X big B from my wife. And in order for me to have a daughter, I have to give her my X. And my X is a little b. So my daughter, Kayla, is considered a carrier. So if a father is colorblind, what do you know about all their daughters? All their daughters have to be X little b. Okay, so what I've just given you here is what we call a pedigree. And if you want to kind of take a step back and see what my parents, so my father is a square, my mother is a circle. Females are always circles, males are always squares. My father is normal vision, so he's X big B Y. And so that means I got my little b from my mother. Now my mother is also normal in vision, so she was a carrier. And so what we do when we find that out on pedigrees, we color them in half. Anyone who's inflicted with the disorder gets totally shaded in. And so here my daughter gets shaded in half. So you can really quickly tell who has the disorder or not. And if you notice here, look, it kind of seems to skip a generation, this type of inheritance pattern. And males seem to get it more often than females a lot. So ALD, we talked about Lorenzo, or watched the Lorenzo video right at the beginning of the year. ALD is also sex-linked. And the boys, so who do boys with ALD always get the illness from? They always get it from their mother, right? It's a very terrible disease. Males aren't going to, individuals with the disorder aren't going to live to reproductive age or to reproduce. And so, the boys are always getting it from their mother. If you recall, Lorenzo's mother was very distraught when she found out that she was the reason why he was inflicted with that disorder. So, I hope you enjoyed the tutorial. If you have any questions on sex-linked traits, be sure to ask your teacher tomorrow.